In this work, we studied the effects of the current light intensity on the mechanical properties of a composite dental resin. We used the dental resin formulation based on 35% organic matrix and 65% inorganic matrix. The monomers present in this formulation are BSGMA and TEC-DMA, which have terminal carbon-carbon double bonds. These are indispensable for the initiation of chain reaction polymerization. The photoinitiators of this formulation are camphorquinone and EDAB as co-initiator. The polymerization reaction is shown on the following diagram. Here, the blue light photon is absorbed by the camphorquinone, but given that the half-life of the free radical is short, the co-initiator is used. Then, the co-initiator absorbs this free radical and then this radical attacks the terminal carbon-carbon double bond to develop a homolytic rupture. Then, this radical attacks other double bonds and initiates a chain reaction that produces a cross-linking polymer. To quantify the light intensity from the blue light lamp, which emits light with a wavelength of 450 nanometers, we use micrometer scale mesh filters. These filters have slit size ranging from 5 to 60 micrometers. Then we prepared samples for mechanical and optical testing. From this testing, we found that an increment of the slit size provided a greater light intensity. Then, with these intensities, we photopolymerized the composites to study the double bond conversion percentages. Now, we focused on the absorbance bands from the alkene and aromatic bonds. We were helped by the FTIR spectroscopy and measured the absorbance before and after the photopolymerization. And with this measure of the absorbance, we calculated the double bonds conversion percentage. In other words, the increment of cross-linking. The double bonds conversion percentage increases with greater light intensity. To test the mechanical properties, we built a machine to measure the specimens with a 3-point test. This machine was programmed and assembled in the lab for this test. This machine interface shows us the stress-strain graph. From this graph, we can calculate the Young's modulus and the flexural stress. From these measurements, we can observe an increase of the stress with greater light intensity, as a consequence of the higher double bond conversion percentage. At the same time, the Young's modulus remains constant because this value is the result of the filler amount, and in our test, we kept the filler amount constant. On the other hand, we can see an increase in the percentage of light transmittance. Nevertheless, the material eventually saturates. These tests were conducted immediately after the samples photopolymerized and then 24 hours under standard conditions. In conclusion, we can see the direct effect of light intensity in the double bond conversion percentage and consequently in the flexural stress. To higher intensities, higher flexural stress.